Let's look at some quantities that look like this. Some base to some power, where b is going to be either a number or a variable, and p will be a number. Now, let's look specifically at multiplying and dividing and taking powers of these types of quantities. These are called exponents. And so we're going to look at what are called properties of exponents and solve problems, basically simplify them down until they look kind of like this at the very end of it. Now, there's a lot of properties to this, but the basic idea is we're trying to expand this whole thing out and then use fast properties to simplify it quickly. For instance, let's look at x to the 5th times x to the 3rd over x squared. Each one of these things, right, as x being the base, is a variable, and a power, 5, 3, or 2, as a number. And we're multiplying and dividing them. So can we simplify this down into a much more succinct expression? And we can. Really what we're doing here is we're expanding all of these powers. X to the 5th is the same thing as x times x times x times x times x. Repeated multiplication is what a power means. Okay? Now x to the 5th is being multiplied by x cubed. There's 3 of them. And that's being divided by x squared. And now you can see, well, we have x's on top and bottom that we can cancel. And there's 6 of these left, which means we can simplify this down to x to the 6th. This isn't too hard when we have, simple problems like this, but what if we start adding in a lot of other stuff, a lot of other variables and numbers in the mix? This becomes a lot more challenging to expand it all out. So if there's some nice rules or properties that can make this faster, that's what we want to do. And there are lots of them. Very helpful to do it. In fact, I recommend whenever you're doing problems with this kind of a flavor here, I recommend looking up a properties of exponents sheet. Just go online and look for that. And it should give you all these rules in one nice little worksheet that you can use. So the first property is called the product rule. And this is where we multiply two exponents. So let's say we had a base to some power m times another base to some power n. Or I shouldn't say another base. They're actually the same base. B is the same number. They have to be the same number. If they are, if you multiply like bases, we add the exponents. For instance, 2 cubed times 2 squared is 2 to the 3 plus 2, or 5 power. I'm going to run through these quite quick because we want to actually start using these in tougher problems. The quotient rule. Here we have some base to a power and the same base to a different power, or the same power, really, it doesn't matter. But in the product rule, right, we multiplied like bases. It led to addition of the powers. Here we are dividing like bases. So what do you think it's going to do to the powers? It's going to take the first minus the second. So let's look at 3 to the 4th over 3 to the 3rd. This equals 3 to the 4 minus 3, which is 3 to the 1. Or in other words, 3. Okay, and the negative exponent. This is just kind of a property of what negative exponents does. It really just flips the thing on the inside. You're going to leave the power on the number because 1 to the 4th power, it does distribute to the top and bottom, but 1 to the 4th power is just 1. And so that's what you get there. This, of course, can also be done in the denominator. This is going to end up flipping it, and it's going to end up being 1 over 1 to the 5 squared, but that's the same thing as 1 times 5 squared over 1. And that's going to end up being 5 squared in the numerator. So it pretty much just moves it from either the numerator to the denominator or vice versa. Think of it like that. If it's in the numerator, move it to the bottom. If it's in the denominator, move it to the top. The next property is the zero exponent property, or let's say zero exponent rule. And this is saying b to the 0 power equals 1, no matter what b is. Everything to the 0 power equals 1. Okay, the power rule. Says that b to the n power and that thing to some other power, or the same one, it doesn't matter, is a power to a power. You multiply the powers. So for instance, say we had 2 to the power of 4 to the power of 5. This equals 2 to the power of 4 times 5, or 2 to the 20. This is actually not too hard to see because 2 to the power of 5 is the same thing as 2 to the 4th times 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 2 to the 4th. And we can look back at the product rule, and the product rule says if we multiply like bases, we add the exponents. So it's 2 to the power of 4 plus 4 plus 4 plus 4 plus 4, which is the same thing as 4 to the power, or 4 times 5. So that's where this rule comes from. Power to a power, we multiply the powers. As a quick aside to the power rule, I wanted to talk about the notation here. This is what the power rule works on. This is 2 to the power of 4 times 5, which is 2 to the 20. This is not the same thing as 2 to the power of 4 to the power of 5. What this is the same thing as is 4 to the power of 5. And 4 to the power of 5 is 1024. These are very different things. What you need to have is parentheses here around both the base and the exponent, and that needs to be taken to a power. This is not what the power rule works on. Just make sure you have these parentheses. You should see the parentheses here, and you'll know the power rule works. So keep that in mind. Now we have product to power. Here, we're going to take a product of two bases, the same power. This power can be distributed over two products, or over a product of two bases. You can expand this out. For instance, let's think about 3 times 4 squared. This is going to be 3 squared times 4 squared. What you can do is you'd say 3 times 4 squared is the same thing as 3 times 4 times 3 times 4, right? That's the same thing as 3 times 4 squared. And we can rearrange this to 3 times 3 times 4 times 4, which gives us 3 times 4 squared. So this just comes back to being able to expand it out and rearrange it. We're really just taking shortcuts with these rules. That's what's so nice about them. Now, product to a power here, we also have a quotient to a power. If we can distribute a power over a product, then we can distribute a power over a quotient. That's because products and quotients are nearly the same thing. And you can, the same kind of reasoning as the product to power rule. You can expand it out and see it out. Now, let's try these rules out on simplifying some problems. So, first one, let's look at 4 to the x cubed times 2 to the x cubed. What I'm going to do is I'm going to rearrange this so the x's are together. 4 times 2 times x cubed times x cubed. 4 times 2 is 8. And here we have two like bases multiplying. So we can use the product rule, which says two like bases that are multiplying, we add the exponents. So we get x to the 3 plus 3, or 6. And that's a much simpler thing to look at than 4x cubed times 2x cubed. X to the 5th times x cubed. These are two like bases multiplying, so we just add the exponents and we get x to the 8th. 6 to the 5th over 6 cubed. Here we have like bases dividing, so we're going to subtract the exponents. 5 minus 3, 6 squared, which in this case we can actually expand to be 36. 8 to the 0 power, well, that we know is 1. Anything to the 0 power equals 1. X squared y to the 4th power. Here we have a product of two bases, x and y, and it's being put to a power 4. This 4 can be distributed to be x squared to the 4th power times y to the 4th power. And now we have x squared to the 4th power. That's a power to a power, so we can use the power rule here, which is power to a power, and we multiply the powers. 2 times 4 is 8. So we get x to the 8th times y to the 4th. All right, 8x to the 5th over 4x squared. 8 divided by 4 is 2. And x to the 5th divided by x squared. We have like bases dividing, so we're going to subtract the powers. 5 minus 2 is 3. All right, let's look at one that's a little bit more involved. Xy to the 5th, and all that is to the 4th power. What I'm going to do here is I'm going to simplify the inside first, and then take care of the outside 4. So we can reduce the 5 on top by 5 and the 20 by 5 on the bottom. The 4, I'm just dividing by 5 on top and bottom there. Now we have x cubed and x. If it's just x, that's the same thing as saying x to the 1 power. So x cubed over x to the 1, we can see that we have x squared because 3 minus 1 is 2. Now that comes on the top. There's a number of ways you can think about it, why it goes to the top. But I could, for instance, I could expand it saying we have 1 on top and x cubed is like this. 1 times x times x times x. And on bottom I have y. Over 4 times a single x on bottom, and then 5 y's are on bottom. And all this is to the 4th power. Okay, now you can see, well, we can reduce by an x on top and bottom and reduce by a y on top and bottom. And we have x squared on top, 4y to the 4th on bottom, with 4 on the outside. Now I don't recommend you using necessarily that strategy, because then you have to expand it, and if you have really large powers, it's going to be very hard to do it. What's important to see is that if you have a higher number on top versus on bottom, then you're going to leave the number on top. So if we do 3 minus 1 is 2, and that's going to end up being on top. Here with the y's, we have y to the, I'm going to use a different color here to make it easier to see, 1 and 5. 5 is the bigger number. So 5 minus 1 is 4, and that goes on bottom. I'll show you a different way of thinking about this that might be a little bit easier, but let me finish this problem the way I've been doing it, and I'll go back. Now we can distribute the 4 onto the insides. That gives us x to the 8 over 4 to the 4th power. It's important to note here that you're not multiplying the 4 by 4. The thing on the outside here, this 4 on the outside, is in the power. And so it's going to be put in the powers of everything on the inside, meaning it's 4 to the 4th power, not 4 times 4. A lot of students make that mistake. So just be aware that it's 4 to the 4th power. You're not multiplying those numbers. And of course, y to the 4th power. That's why I should have written that on top here. X squared to the 4th power. Now, power to a power, we just multiply the powers. 2 times 4 is 8. 4 to the 4th power. 4 squared is 16, so 16 squared is 64. No, that's not right. 16 times 16 is, I think, 256. And then y, 4 to the 4, we multiply those things and we get 16. Okay, let me show you a slightly different method for doing this. Makes it a little bit, I think a little bit more understandable. Let me just clean this up a little bit so it's easier to see. And that's 20 there. Now, I'm going to again reduce the 5 over 20, but now I'm going to write it as 1/4. And we have x cubed divided by x is x squared. Okay, 1/4 times x squared. And y over y to the 5th. This is y to the 1 over y to the 5th. That's going to be y to the 1 minus 5, which is y to the negative 4. We're going to multiply this by negative 4. And this goes to the 4th power. Now we can distribute this into all the numbers here. Again, we have 1/4 to the 4th power, not multiplying by 4. X squared to the 4th power, and y to the negative 4 to the 4th power. Now we have 1/4 times 1/4 times 1/4 times 1/4. That's going to be 256. X squared to the 4th power is x to the 8th power. And y to the negative 4 to the 4 is going to be y to the negative 16. Now, typically, problems will ask for no negative exponents. That's because negative exponents are harder to work with than positive exponents. So we want to get rid of negative exponents by either moving them to the numerator or denominator using the negative exponent rule, which just flips it. We have 1 over 256 times x to the 8th times 1 over y to the 16th. And we can multiply this all out, right? X to the 8th is over 1, and we get x to the 8th over 256 y to the 16th. And we get the exact same thing we got previously here, which you should expect that. Whichever way makes more sense, I recommend doing that. But the bottom way is probably more aligned to being easier for more difficult problems. If you have large exponents in the first way I showed you doesn't quite work out nicely. So it's up to you which way you want to do it. All right, let's look at some more. 7 to the negative 2. Using the negative exponent rule, we flip it, and 7 squared is 49. If you can't expand the number, unless it's some really, really large number like 2 to the power of, 140, that's going to be too big of a number to write out. But if you can't expand it like this, in this case 7 squared is 49, do so. All right, 1 over 2 to the negative 4. Negative exponent rule means it flips to the top. Of course, we can just drop the division by 1. and 2 to the 4th power is 16. All right, we got j to the negative 13 times j to the 4, oops, that's y, times j to the 6. Looking back at the video, I made a mistake doing this problem. I said that j to the power of negative 13 times j to the power of 4. This gives you j to the power of negative 11, which is not true. It gives you j to the power of negative 9. So I just wanted to redo that here. For doing this problem, what you want to do is you want to take this in parts. So first off, j to the negative 13 times j to the 4. These are like bases multiplying, so we add the exponents. So we have negative 13 plus 4. Negative 13 plus 4 is negative 9. And this is multiplying j to the 6. And again, we have like bases, so we're going to add the exponents. Negative 9 plus 6 gives you negative 3. And you would say not have negative exponents. You put that in the denominator, j to the 3 over 1. So that's probably what you want to see. Sometimes that would be acceptable. All right, 24x to the 6 over 12x to the negative 8. Here, I'll kind of do the second method that I showed you before. 24 divided by 12 is 2. X to the 6 divided by x to the negative 8. We have division of like bases, so we're going to subtract the exponents. So we get x to the 6 minus negative 8, which means we have x to the 6 plus 8, or 14, which is just x to the 14 like that. All right, now a long one. A squared b cubed c to the 0 all over 3 a cubed b to the 4th c cubed to the power of negative 4. Okay, let's simplify the inside first, and then we can deal with the negative 4 on the outside. The numbers can't simplify at all, so I'm just going to leave them as negative 7 over 3. Now we have a squared over a cubed. 2 minus 3 is negative 1. B cubed times b to the 4th, 3 minus 4 is negative 1. And c to the 0 over c cubed is going to be 0 minus 3. We get negative 3. Now we can distribute the negative 4 into all of the powers. So we get negative 7/3 the negative 4 times a negative, I'll just write it out. All of these things have negative 4 as an outside power. Negative 3 to the negative 4. And this first one, the negative is going to end up flipping the inside. Now, since we have a fraction on the inside that's not, a single number, all we're really going to do is we're going to flip the numbers. So it's going to be 3 over negative 7 and put both of them to the 4th power. It's going to be 3 to the 4th power over negative 7 to the 4th power. So you see how I flipped the numbers? That got rid of the negative in the exponent, and then I distributed the 4 to get rid of, distribute the 4 so that I can actually calculate some more stuff here. Okay, negative 1 to the 4th power, to the negative 4th power, we multiply the powers. Negative 1 times 4 is 4. The same thing for b. b to the negative 1 to the negative 4 is going to be negative 1 times 4. And c is to the negative 3 to the negative 4. It's going to be negative 3 times negative 4, which is positive 12. Now you see that a, b, and c are all positive exponents, so they can just go on the top. 3 to the 4th power is 81. That's a nice, easy number to write down, but 7 to the 4th power is going to be a long one. Well, I can still write it out. I got plenty of room there, so I'll use a calculator. And a negative will end up canceling because negative times negative is positive, times negative is negative, times negative is positive. There's 4 negatives there. So we get a positive number, 2401. And that is a simpler expression to look at than this starting kind of mess that we have there. That's a much better thing to work with. All right, the last topic for this video I want to touch is scientific notation. A lot of times we want to simplify numbers and expressions down to an easy to read format. And this is true for very large and very small numbers. We use a scientific notation to write it in a much more easy to understand, clearer way, just for our human readability. So let's take this scientific notation, 9.2 times 10 squared. Our number system is base 10. That's the reason why we have a 10 to some power there. And 9.2 is a much easier number to look at. And 10 squared, once you get a hang of what that scientific notation means, 10 squared can tell you what's the magnitude of that number. And so let's write this number in decimal form. Well, 10 squared is just 100. So 9.2 times 10 squared is a 10 to the 100. So really we're just moving the decimal point over 2 spaces. We get 920. When you have a positive number here, we're going to move this thing that many spaces. If it's negative, we're going to go the other way. This would be negative. Okay, let's look at another one. Negative 8.17. Oops. 8.17 times 10 to the 6. This is a positive number, so we're going to move it 1, 2, 3, 4, 5, 6. Every spot that's not filled with a number, we're going to fill with a 0. So we get negative 817, 1, 2, 3, 4 zeros. That's how many were not being filled here. So negative 8.17 times 10 to the 6 is negative 8,170,000. Again, negative 8.17 is a much easier number to work with, and 10 to the 6 tells you that it's a million because it's 6 spaces, 6 place values larger than the 1 place value, which is the millionth spot. All right, negative 3.14 times 10 to the negative 3. Here we have a negative exponent, so we're going to move the other way. 1, 2, 3. Of course, the negative doesn't count for a spot. That's just a sign. We're going to add zeros there, and we're going to move the decimal to that spot. So you always should add a 0 in the beginning for kind of a place values idea. We have 2 zeros and then 3, 1, 4. So negative 3.14 times 10 to the negative 3 is the same thing as negative 0.00314. And again, you can make sure you're doing this correctly by counting the spaces. If this is where the decimal goes, 1, 2 gives us 9.2. Here, 1, 2, 3, 4, 5, 6. So 8.17. Here we have 1, 2, 3. And so we should always count the same number of spaces that's in the power of the 10 to some power. All right, here I've got 2 numbers that I want to write in scientific notation. So I'm going backwards here. I'm going to go this way instead. So the way we do this is quite simple. Find the decimal point and then calculate how many spaces to just after the first number that's not 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That gives us 6.38 times 10 to the 17. Which is much easier to work with than writing out this long number. Okay, the same thing is true for this decimal number here. We find a decimal point, which is right here, and we go 1, 2, 3, 4, 5, 6, 7, 8, 9. This is negative 4.05 times 10. Now we move the other way, so we're going to give it a negative 9 here. So a negative power in the exponent means it's a very small number. It's going to be a very decimal, long decimal number here. A positive number in the exponent means it's going to be a very big number. So in this case, it was what, 1,000, million, billion, trillion, quadrillion. So 638 quadrillion. It's a very large number. Now, if we were to multiply or divide these numbers, we can actually use rules of exponents on them because we have 10 to the power of something, which is an exponent. Let's look at a couple of these problems and see how to do it. So here I have two scientific notation numbers multiplying together. I'm going to rearrange this so that I have the number parts together because they're all just multiplying. So I can rearrange this quite easily. And then we'll get the exponential parts together. Now I have 1.4 times 3. 1.4 times 3 is, let's see, 4.2. 14 times 3 is 20, yeah. And then this is going to be times 10 to what power? Well, we have two like bases multiplying each other, so we add the exponents. 15 plus a negative 11. That's going to be 15 minus 11, or 4. And that's in proper scientific notation. There's the decimal point is right after the first non-zero number, so that's good to go. If it was anything else, we'd have to kind of rearrange it. All right, this one is going to be division. 1.5 times 10 to the negative 2 over 3 times 10 to the negative 16. Sorry, negative 6. Here we have 1.5 divided by 3 is going to be 0.5. Plug into your calculator to make sure of that. And now we have 10 to the negative 2 over 10 to the negative 6. Those are like bases dividing each other. So we're going to subtract the exponents. 0.5 times 10 to the negative 2 minus negative 6 is plus 6. It's going to be negative 2 plus 6 is 4. This is not in correct scientific notation. That's because this decimal point is not right after the first non-zero number. The first number there is 0. So we actually need to move it. Move it one space here. Now, what does that do? That's going to end up changing the power here. And it might be confusing which way it changes it. I get confused by it. So I recommend, instead of kind of trying to figure out the properties for that, I recommend just expand this number. 0.5 times 10 to the 4 is going to be 1, 2, 3, 4 spaces. So 5,000. And then recompact it into the scientific notation. 1, 2, 3. This is the same thing as 5 times 10 to the 3. That's the method I recommend using. There are tricks to what you can do there so that you don't have to expand it and subtract it or compact it again. But it's prone to error, so I recommend do it this way.